So let's start talking about this vocab. So this is the term domain that has started coming up. I already gave you 2.3, right? 2.2 is what I need to pronounce for you later after we get started. Cool. Alright, so we should have 1.9 to 1.11 self-assessment ready. That's this one that I gave you all yesterday. This is the only homework I asked you to do besides that the domain vocab. Do you all have this self-assessment ready to turn in? No? Totally forgot about it. So you're going to get it done this weekend on top of the normal homework, right?
Yes.
Yes, sir.
Okay.
You have them all.
Are you serious? What? You don't have to do it, Anthony. You already did this. But yes, you have homework for me, like... I feel like we should be used to the fact by now, right? There's no excuse.
The first match each other ever had to do that though.
What, homework on the weekend or homework in general?
Homework in general.
Oh,
Except for Miss Coy, I had homework like you.
For who? Who do you have homework for?
Oh, Miss Coy was the only math teacher I ever had homework for besides you.
Yeah.
Miss Hodger never gave us homework.
Just who?
Miss Hodger.
Yeah. We just have different philosophies of certain aspects of education.
No, I fell asleep.
I was the smartest person in Miss Hodger's
My last
class.
period was first.
Yeah?
I ran the mile
believe
last
that?
period, so I was so tired when I got home.
I don't know. I wasn't in there.
I didn't do that.
99.
I couldn't.
Alright, hey guys, let's go over this vocab quickly and then we'll get started.
Yes, sir.
So one thing I do want to remind you about, because this is something I feel like we consistently forget. One, this vocabulary graphic organizer is designed to help you take notes about where stuff can be located, right? Examples and notes. Because this should be your study guide. This is also something that you should always be able to pull out in the middle of any task and use it as a resource. Because we're going to record notes here to help us understand concepts. And that might be extremely helpful today when we look at the idea of continuous versus discrete, linear and exponential, different things like that. So, but domain, hopefully we have some ideas. Actually, first off, did anyone do vocab last night before I waste my time? No. All right, I'm going to check for homework on Monday then. Guys, you cannot learn well if you spend no time reflecting on what we've done in class. This isn't even asking you to do a whole bunch of problems. I'm asking you to define one single word, create a personal definition, try to find some connections to prior learning into the real world, and just identify where you could find examples and notes. I need you thinking about these things. It is through reflecting upon what you have learned that you are going to truly understand. Please notice that. I'm not just saying about earning a 99 or anything. To truly understand, you have to spend time reflecting upon what you have learned in class. You want to get better? You want to understand? You want to never be lost? You have to reflect upon what you're learning. Okay? That's the design behind this graphic organizer. But you got to get it done. So we're not going to go over this today. We'll go over it on Monday. That kills me. All right. So we're going to launch, we're going to look at the objectives, and we're going to launch 2.3, and for the most part, we might go over one or two of these together at the beginning, but the rest of this, for the rest of the task, it's going to be you working in your small group. I would keep your vocabulary sheet out and use it as a reference sheet. Maybe even pull out your previous tasks to help you think about these things. Okay?
Oh, wow.
What?
Graphs.
Yeah, Alan, you said you want to do the objectives today, right?
I can identify linear and exponential functions and justify my response.
Okay, so we want to be able to identify linear and we want to identify exponential functions. We've started talking about this already with 2.1 and 2.2. So if you need some help with your group or with the discussion, go back to the old tasks to reference those things to help you learn it better. So I think this is a great one to start on. Number one, linear, exponential, or neither.
Linear.
Okay, what is your justification that it is linear?
It's a straight line.
Okay.
That's basically it. Because if it was exponential, it'd have a curve in it.
So graph shows a straight line. Okay, exponential would have a curve in it, But how do you know it's not neither?
We wouldn't have a line at all.
Okay, we need a little bit more.
Yeah.
Is there,
Is it,
Stuff in
does it have
between?
an additive rate of change?
that'd be,
Well, there is stuff in between, which makes it what type of model?
Continuous.
Continuous, right? So I do want you to notice, you need to give at least 2 reasons for your answer. That's something pivotal here, right? So we have one really strong answer right now, but McKay, what were you just saying with that idea?
Does it have an additive rate of change?
Does it have an additive rate of change? Notice I'm only given 2 points here, but could I possibly figure out what that additive rate of change is and see if it gets me other points on this graph?
Yeah.
Yeah. First off, what would we call that additive rate of change?
Common, common difference.
It is a common difference, but there's a more common word we use when it comes to a linear function.
Arithmetic slope.
Slope, right? The common difference, if you go back and you look, the common difference is really built off of the tables for sequences. Because remember, with a sequence, is a sequence continuous or is it discrete?
Discrete.
It's discrete. So are you going to have anything in between those values? No, so the difference between those values is 4. Now, if I were to graph it, that means my slope is also 4, but can you get stuff in between when you have a slope?
Yes.
Yes, right? A slope allows me to get things in between those points. A common difference doesn't really. A common difference is just telling you how far it is to the very next point. So how are we going to calculate this slope?
Rise over run.
Okay. Now, and I know this is going to sound nitpicky. This is not being nitpicky. This is just to help you work on your language a little bit better so we can communicate mathematics a little bit better. A lot of people, and I even have to catch myself saying this, a lot of people, they'll say rise over run. But over is not a mathematical operation.
Divided by run.
There you go, right? We want to be intentional about that language and understand that that's important. It's not just over something. Over is not mathematical, but it is the rise divided by the run. It's a ratio of the change in y to the change in x. Okay?
I think we learned it like that because we wouldn't get them swapped around because rise is above run.
I could see that, but even if you were to say rise divided by run, the only thing you're dividing by is run. To be honest, and I think this is what it really is, it's very common or just, I've heard teachers forever say rise over run, and then teachers just teach the same thing that they were taught instead of critically pushing on and saying, is that mathematically appropriate, right? And it's important to pay attention to those small details because they can change the way, change how well we actually understand what's happening.
We can say run over rise.
Well, you're definitely not doing run over rise. Okay, but rise divided by run, so what is my rise in this case?
Point. Wait, never mind.
Like, is it going up 0.5 or is it going down 0.5?
Up 0.5.
Okay. So positive 0.5. What's the run then?
Run would be -3 or divided by 2.
So -3 divided by 2?
Yeah.
Okay. So here's a couple things I do want to point out. Not in any way, shape, or form that you're wrong, but notice the way that McKay is seeing this is you're going from this point up 1/2 and to the left 3/2. Would it have been okay to go down and then to the right? Would it have changed the slope at all? So let's check it, right? We're going to look at this in just 1 second. We're going to do the brown one first. But notice how I wrote it as fractions. Is it easy to do a decimal and a fraction at the same time?
No.
Is it even easy in your head to do 2 decimals at the same time? No. And this is why, and I know a lot of students are scared of fractions, but if we understand how fractions work, this can help us a lot. First off, how do we divide by a fraction? Does anyone know that? You're going to multiply
Bottom two.
by what?
You can multiply the bottom two.
You don't multiply the bottom 2. I'm not quite sure what you mean by that.
Me neither.
I think you're thinking about when we multiply fractions. If you multiply fractions, you would multiply the numerators and you would multiply the denominators.
That has a common denominator.
Well, do you need a common denominator to multiply?
No.
Mm-mm. Only need common denominators when we're going to add or subtract. And the reason for that is, if I were to look, well, first off, do y'all know why that is, why we need common denominators?
Nope.
Just been told you need that your entire life? Okay?
Never been taught fractions, really.
That's really hard to hear. I hate that. They're so good. Alright. I know that sounds dumb, but it's true. So here's 2/3. Notice how I'm shading in 2 of the 3 pieces? Now here's 1/2. Can I easily add those pieces together?
Nope.
I mean, does that one piece equate to this one piece?
No.
No. That's why you need a common denominator. Notice how there's 3 pieces here and there's only 2 here. So I'm going to split each of these 2 into 3. And I'm going to split each of those 3 into 2. Now, does each piece correspond to the pieces below it? That's where the idea of a common denominator is coming from. Notice how I had it split into thirds. So I split it into halves. I had it in halves, so I split it into thirds. But I'm multiplying by 2 divided by 2 because that's just the number 1. So I'm not changing its identity. But notice how that's 4/6. Is that what I had here? 4/6. Yeah. 1/2 splitting into thirds, so that's going to be 3/6. Is that how many pieces I had down here? Now, because I have the equal sized pieces, I can just add them. So here I have 4 of those 6. Here I have 3 of those 6. So in total I have 7/6. That's true for both adding and subtracting fractions. That's where that's coming from. Does that help make it make a little bit more sense? But when you're multiplying, you are just multiplying straight across. I'd have to sit down and think about it a little bit longer to explain it using this notation. But I do know that I can make it work. I just haven't done it in a long time. But you multiply across the numerator, across the denominator. However, when you divide by a fraction, now this I can explain pretty quickly. Let's just say I have 2 being divided by 1/3. You should remember this because we've talked about it before. Division is repeated what? Not multiplication. Subtraction. Remember, repeated addition is multiplication. Repeated subtraction is division. Now the one caveat to that is it's repeated subtraction until you get to 0. Okay? So if I do 2 divided by 1/3. So what am I repeatedly subtracting away? 1/3. Okay? Oops. So how many 1/3 would I have to take away until I get to 1? 3 of them? How many more 1/3 do I need to take away for another 1? So notice that's taking away 1, that's taking away 1, and now I'm at 0. How many 1/3 did I have to take out? 6. Notice that's the same as 2 times the reciprocal of 1/3. Okay? And the reason why is, or another way to think about it is visually, we have 2 holes, right? We're splitting those 2 holes up into how many pieces? Which I am terrible with these. I should have gone back to the rectangles. Fun fact, oftentimes we do this with circles. I always use rectangles because I'm so bad at drawing thirds in a rectangle,
No, you're not.
or in a square. Circle, that thing, words. Okay, so I've got a rectangle here. I'm splitting my rectangle into thirds. How many thirds do I now have?
6.
6 of them. Right? So again, when we divide by a fraction, what you really do is you multiply by the reciprocal.
So basically, you just flop the fraction and multiply the top number by.
So let's be more clear with our language. What is it called when you flip the numerator and denominator? There's an R word.
Reciprocal.
Reciprocal, right? So to divide by a fraction, we multiply by its reciprocal. Okay? Now I will point out there's a couple ways you can approach this. 1 times negative 2 is negative 2. 2 times 3 is 6. And so you can just do that and then simplify. What I personally would do though, is I would say, hey, what is 2 divided by 2?
4.
Divided by 2.
Negative 2. 2.
Okay.
1. Right?
Oh yeah.
So this would be left as a negative 1. This would become a 1. And what's 1 times negative 1?
1. Negative 1.
Negative 1. What's 1 times 3?
3.
So by simplifying first, I've made my job easier. Right? I simplify first instead of later. But you can do either one you want. Okay, so notice though, can you grab the door? Thank you, Anthony. So please notice though that my slope then is negative 1/3. So I'm going down 1 over every 3. Or I really could even keep it as going up 1/2 and over to the left 3/2. Either one of those would work. All right, so I can go up another 1/2 and to the left 3/2. Is that a point on the line? Yep. From here, could I go down 1 and to the right 3? Is that what it was? So, well, 1, 2, 3. Is that a point on the line? From here, could I have gone down 1/2 and to the right 3/2? Oh yeah, it ended up right there as well. So notice, do we have this idea of a slope of negative 1/3 or 1/2 divided by negative 3/2?
Yeah.
Is that evidence that it is a line?
Yeah.
Yeah. Right? So graph shows a straight line. Perfect, right? We're just looking at the graph, but getting a little bit more into the weeds of it, noticing, hey, if it's linear, it has that additive rate of change of a slope, right? Additive rate of change of m equals negative 1/3 yields more points on the line. Okay, so we had our fun little exploration into fractions for a second, but this is really what we wanted to get back to. Okay? I'm going to leave this up here. You should be able to take some notes on this, and I'm going to let y'all work for a little bit on the next few problems on your own, and I'll come by and listen in on your conversations. But those are critical things to notice, right? Notice by not just doing one reason, but by doing two reasons, we had to go deeper into our understanding of what does it mean to be linear? What does it mean to be exponential? So you need to have at least two reasons to really force yourself to think, hey, is it linear, or is it exponential, or is it neither?
Yeah, you could go up to 3 house.
You could also what?
You could also go up to 3.
Go up to 3?
Yeah.
What do you mean?
Instead of going down 3.
Well, I didn't go down 3. Remember, the slope was negative 1/3. So I could go down 1 and to the right 3. Or I could have gone, notice I could have assigned the negative to the denominator. But notice that going up 1 and to the left 3 is how I got that point. We just need to remember, rise is in the numerator, run is in the denominator. Okay? So go ahead and start working on that within your groups. We're working on number 2. I'll leave this up here for now if anyone needs to write that down as you get started. But this is definitely a day to be talking within your small groups and to be helping each other out.